All right, all of our hard work is leading us to the convergence theorem. All of your work last night, that 29 to 42, all of your answers were numeric, yes? They were some kind of number. Either the number was 0 or it wasn't, or it was greater than 1 or less than 1 or equal to 1, but they were all numeric. What we need to do today is we need to generalize it to talk about what if the limit is algebraic. So what's the difference between a numeric limit value and an algebraic value? Variables. We've got variables. Okay. All right. If the limit value is algebraic, so it's got some kind of x in it still. We'll call it L, even though it is algebraic. So if the limit value is algebraic, we'll say L. Then what must still be true about L, even if it is algebraic, in order to guarantee convergence? Yes, very good. Okay, then the absolute value of L must still be less than 1 in order to preserve convergence or to guarantee convergence. All right, so we've been establishing that from the very beginning. If the geometric series had a ratio that was between, okay, the ratio is the same thing as what the limit value would be. If that is, the absolute value of that is less than 1, we know we have convergence preserved. So you're going to start with that algebraic. Now you're going to have some algebraic work to do. You're going to manipulate that limit less than 1 until it looks like this. Absolute value x. In other words, you've got to get that x by itself minus some kind of center, and then we're going to call that capital R. Now it's frustrating because this capital R is not the same thing as remainder. It means radius. Now, so you're going to manipulate that limit, whatever the algebraic result was. So add or subtract to both sides, multiply or divide to both sides until it looks like this. R is what we call the radius of convergence. A is what we know to be the center already. A is the center of the interval of convergence. So A is that focus point, like we're focusing on this particular point. At this point, and the radius being this much to the left and this much to the right, within that is where convergence will happen. So when they are talking about radius, that's what they mean. It's the value that you get when it's in that form. Then if you get x by itself, you can make it look like this. Once you have the r, then you can take off the absolute values, and you'll have negative r on one side is less than x minus a, which is less than positive r. That's what a radius means. Some to the left, some to the right when you take off those absolute values. And then how do you solve for x by itself? Add a to everything. So then that is true, and then we can add a to all terms. So negative r plus a will be less than x by itself, which will be less than positive r plus a. And when it's in that form, the definition of that is called the interval of convergence. So you've got your radius of convergence and your center of convergence, and the two of those together combine to make the interval of convergence. All of this language we've already talked about, so that should not be new to you. So I'm going to put a box around this to identify it is the convergence theorem, and we'll put it into practice. We're just working with algebraic stuff now instead of actually with numbers. So here's how that's going to put into practice. All right, if the following summation going from 0 to infinity of the expression n, or of the series n x to the n over 10 to the n, if it converges, then find the radius and the interval of convergence. So first, we have to find the limit. That's where we start. The limit will be algebraic. That algebraic limit must be guaranteed to be less than 1, and then we'll proceed from there. So let's set up the limit as n approaches infinity to test for convergence. What test do you think would be the best option here based on kind of your experience of what you worked with yesterday? Okay, because it's got exponential. Okay, exponentials and factorials really work best for ratio test. All right, so we're going to set up the ratio test using n plus 1. So that's going to give me n plus 1 x to the n plus 1 over 10 to the n plus 1, and then multiplied by the ratio of 10 to the n and x to the n. And then we're going to simplify and reduce. Things with the same bases will reduce. And so the 10s will reduce. The 10s will reduce this way. The x's will reduce that way. So we are left with n plus 1 over n, which don't reduce. We'll be left with x to the n, just x, and just 10. The value of that limit, when I plug infinity into not x, but plug infinity into n, I'm going to get infinity plus 1 over infinity times x over 10, which is infinity over infinity, which means I need L'Hopital one time. And when I take L'Hopital, I'm going to get 1 over 1 times x over 10, and there's no more n's left, so the result is x over 10. So the result of the limit is an algebraic expression. I need to make sure that that algebraic expression, as its limit, stays less than 1 in order to guarantee convergence of this series. To find the radius, I need to manipulate that so that x by the x term doesn't have a coefficient. So I'm going to multiply everything by 10. And so I can tell now that the radius is how much? 10. What's the center? Okay, so my radius of convergence is 10. That's pretty big. The center is 0. And the interval of convergence is what you get when you remove the absolute values. So negative 10 to 10 is the interval. So this series will converge as long as x is between the values of negative 10 and 10. If x is outside of the values of negative 10 and 10, then the series will not converge. And so you're solving for an algebraic expression that will guarantee convergence. Questions on that one? Okay, so let's try another one. All right, so we're going to do the same thing to the following series. So n is 0 to infinity of n times 4x plus 3 to the n over 2 to the n. So we need to find the limit. Again, probably the best test to use is going to be the ratio test. So applying the ratio test, by the way, on an FRQ, it is going to be really helpful and earn you points if you identify just what test that you're using. Sometimes it's like score. You get really lucky, they'll tell you what test to use. Use the ratio test to prove the convergence of, and you're like, yes, thank you very much, you told me. But if they leave it open-ended, try and identify what test you're using. All right, so the limit, so we will have n plus 1 times the quantity 4x plus 3 to the n plus 1 over 2 to the n plus 1, and then multiplied by 2 to the n, regular n, 4x plus 3 to the n. So once again, we're going to reduce things that have the common bases. So what don't reduce is the n plus 1 and the n. Those don't. The 2's will, and the 4x plus 3 will. So I will be left with, oops, a single 4x plus 3 in the numerator and the value of 2 in the denominator. And just like last time, this will need L'Hopital because I end up with infinity over infinity. So applying L'Hopital by taking the derivative of the n terms, I will end up with 4x plus 3 quantity over 2. And then there's no more n's left. All right, in order to guarantee the convergence of this interval, I need to establish that the absolute value of this result, this algebraic result, must be less than 1. In order to find the radius, I'm going to need to manipulate this so that the x coefficient is 1. So I'm going to multiply by 2. So I get 4x plus 3 is less than 2. And then I'm going to divide everything by 4. So that's going to give me x plus 3/4. Absolute value is less than half. At this point, I can identify what the value of the radius is and where it's centered. And so I can tell that my radius is 1/2. I'm centered at 3/4. And so this is a much smaller convergence interval than the one I had before. The one I had before was from negative 10 to 10. It was a huge convergence interval. This one is going to be much smaller. What did I? Yes. Okay. And so then we'll take off our absolute values to find the interval of convergence, and we'll subtract 3/4 from everything. So I'll get negative 5/4 is less than x is less than negative 1/4, which is my interval of convergence. So this series will only converge for x values that are between negative 5/4 and positive 5/4. Anything outside of that as an x value will result in a divergent series. We only have convergence guaranteed within this interval. Okay, how are we doing? Okay, good. All right. If the series is geometric and convergent, find the sum. Okay, if the series is geometric and convergent. All right, well, if it's geometric, how do we know it's convergent? What about it has to be less than 1? Not its limit, but its multiplier, right? Which is actually the same thing as the limit. If you take the limit, you're going to get the multiplier. Okay. All right, so if we have this one, n equals 0 to infinity of x minus 2 to the 3n over 8n. You can recognize this as being geometric because the n's are the only thing in the power. Like the only place n happens is in the power. Like compared to the ones we had before, there was an n in the power and there was an n as a coefficient. In the first one, same thing. We had n as a power and n as a coefficient. For this particular one, you can recognize it's going to be a geometric because they share the power of n. And so another way to write that is to write it as the shared power of n. So the denominator will be 8. What will the numerator be? X minus 2 cubed. If the entire expression can be multiplied as something to the n, that's got to be a geometric series because everything is just going to be multiplied by x minus 2 cubed. Yeah, so we have little r being the multiplier. Yeah, we have little r. Okay, so little r must be less than 1. If you didn't recognize it and you did the ratio test anyway, you'd still get the same thing. So there's not really, don't get all stressed out like, well, what if I miss it? Even if you miss it and you do the ratio test, you're going to get x minus 2 to the third over 8. It'll still work out. All right, so our multiplier of x minus 2 to the third over 8 must be less than 1. So multiply everything by 8. So x minus 2 cubed must be less than 8. Take the cube root of everything. Didn't that work out nicely? X minus 2 is less than 2. So we can tell what our radius is, and we can tell what our center is. So radius 2, center also 2. Our interval will go from 0 to 4. So this thing will converge. It's geometric as long as x is between the values of 0 and 4. Now find the sum. So we learned before that our definition is the first term over 1 minus r. Okay, we learned that as the sum of a geometric series. So what would a to the a sub 1, the first term, be? Well, look back at the original problem. Plugging in 0 will give us the first term. And if I plug in 0, what will I get? 1. Okay, so that's my top. And then 1 minus, and little r is what I had determined the multiplier to be. So that would be minus x minus 2 cubed over 8. So the sum will be algebraic as well. The sum is not going to be a number. The sum is going to be an algebraic term. So 1 over 1 minus, all right, now expand x minus 2 cubed over 8. You guys remember how to do that? Okay, x cubed, then what? Not 4, it's going to be a 6. Yeah, it's 1331, but I'm using the number 2 as well. So this is going to be 2 times 3x squared plus another 3, 2 squared times 3, and that's x. And then the last one is minus 2 cubed. So it simplifies to be, that's using Pascal's triangle, 1 minus x cubed minus 6x squared plus 6x minus 8 all over 8. And then you just do some simplifying algebra. I think I'd want to multiply everything by what number? I'd multiply everything by 8. So I'll have 8 over 8 minus x cubed plus 6x squared minus 6x plus 8. So I multiply everything by 8 and I distributed the negative back into my interval, back into the quantity. So I'll have 8 over negative x cubed plus 6x squared minus 6x plus 16. And that will be the sum.
Is it 6x or is it 12x?
Oh yeah, right. I can multiply. Thank you. It's not just 2 times 3. Thank you. It's 2 squared. It's not just 2 times 3. It's 2 squared times 3. So 12. 12. Thanks, Aubrey. Okay.